All right, y'all, we are going to talk about rational functions today, and we're just starting this 1-6 we're going to cover over the next 2 periods. So a rational function, kind of like its name, rational, just means that you can write the function in some sort of fraction. So you're going to be exploring this rational function here in regards to the context given. I'm going to have you attempt problems 1 through 6 on your own. And then when you come back to the video, you can look at some suggested answers. You may not have exactly the same thing, but then I'll have you add some extra notes. Okay, so pause the video and try 1 through 6 now, please. Okay, here are some suggestions for too little or too much anesthesia. What I want to talk about more is this graph. So we've got an interesting shape here. Starts at 0, spikes up, and then comes back down. And it's not coming down at the same rate as it was going up. And it appears to be leveling off. Okay, so leveling off for graphs usually means there's some sort of asymptote. So maybe you wondered how long will it take for it to be gone? Like, does it approach 0 there? Or maybe you asked, is there an asymptote showing up? Or will the anesthesia ever be considered gone? Okay. Concentration was represented in percents, and you may not have recognized that at this point because they didn't do a good job about how this concentration was measured here. It wasn't until the next problem where it talked about the concentration reaching 5% that we realized that the y-axis was in percent. Okay, so if you didn't get that label on there, that's not your fault. Really, they could have done a better job with that. But go ahead and label this graph that as percents. The other part they did tell us T is in hours, so we can add that here. Oop, a little too far there. So if we go talk about that graph a little bit more, there were 2 questions being asked. Okay, the first one was, what was the concentration at a half hour? And we talked about that being 3%. And then another thing dealing with the graph is when it reaches 5%. So I'm going to go back and talk about those 2 items. Okay, the half hours are right here up at the value of 3%. And then 5% is really this horizontal line where the anesthesia equals that 5%. And it intersects in 2 different points. From there you can go grab the 1 hour and the 6 hour. So between those 2 times it was all good. After that, not so much. Okay. In fact, not so much in the too little anesthesia, we could have that patient waking up. So mathematically, that's where this 4 is really coming from, or from the graph. But when we think about the algebra, because this is the y value, we're acting as the y value, that's setting our equation equal to 5. And I did it on the left just because that's where this c of t was, which replaces our y. But you could have just as easily put it on the right-hand side. Remember, to get rid of this denominator, we practice lots with that. You just multiply on both sides, distribute through. And we practice factoring for this reason. Okay, when we see this squared show up, we have a quadratic equation, and factoring is a strategy to solve these. Okay, the ones we are going to be working with are going to be, the majority of them at least, are going to be rational, where we can factor them. If you use quadratic formula at this point, that would have been fine because I didn't specify. That is a technique. But remember, if you are factoring, step 1 is to look for a GCF. There was one. And after taking that out, it was easy factoring where you could just do T and T. If in the case you didn't catch that, you might have factored by grouping and it looked like maybe 5t minus 5 and t minus 6. Or similarly, it could be 5t minus 30 and t minus 1. But then again, there's a GCF that can be taken out to make it one more step better. No matter what you did, you should have gotten the answers 1 and 6 matching up to the graph there. Here, after time passes, it should get smaller and smaller until it's gone completely in theory. It didn't look like it was hitting 0 from the original graph, but in theory, the anesthesia, something we're putting into our body, should dissipate after time. Now, mathematically, though, when we talk about this equation, it doesn't actually get to 0 again. Okay, and how we know is maybe you thought about the end behavior with an asymptote. It gets close to it, but it doesn't touch. But we're going to talk about that end behavior gets closer to and doesn't touch isn't necessarily true. It can actually touch. In this case, it was 0 at one point. That doesn't mean there's not also an asymptote at y equals 0. There actually is, and we'll talk about what about this equation makes that true. But mathematically, here's how we set it up. When we want the anesthesia to be 0, that's a y equals 0, and we can solve it the same way. Okay, so you may have just explained this in words, but I want you to go ahead and write this math down. Okay, when we do this and solve it the same way we did over here, okay, multiplying that over on both sides, 0 times anything eliminates that fraction completely. So it just says this 35t equals 0. So it's really the top part that is going to give me where that y value is equal to 0. And that's going to be a helpful tool as we work through critical values of these equations. But that gives us t equals 0. If you go back to the graph, the point 0, 0 was on there, but then there is no other place mathematically that it will actually hit 0. Okay, so it did start at 0, but never touches it after that again. So there may be an asymptote here, I'm telling you there is, but it touched that value too. Okay, and that can happen. So we're going to talk about all of the different things that rational functions can show up. We're thinking of it similar to the parent function 1 over x or 1 over x squared. So there are asymptotes that are going to show up in fractions, and we're going to talk about the different types. Okay, we'll start with vertical because that is something that we have practiced a ton as it comes to conversations with domain. Okay, remember, vertical asymptotes are where x can't be, and we're going to talk about how we find this just in an example. Okay, so if we have a vertical asymptote, we know it's x equals something, but that something comes from, if we think about our parent function, y equals 1 over x, it's what makes that bottom part of the fraction 0, because we can't divide by 0. So this value is going to come from finding the restriction or setting the denominator equal 0. Okay, because we cannot divide by 0. This is a restriction in the domain. Okay, but then we also have horizontal asymptotes. And what I'm going to do is split these into 3 sections. Now, only 2 of them are technically horizontal, so we'll talk about those first. And then there's another one where it's something different entirely. Okay, so when we talk about fractions with rational functions, we could have a constant on the top, but there's no guarantee that there is. If we go back to the equation that you were given, it had a 35t, which is a line on top, and a t squared plus 6 on the bottom, which is quadratic. So in this case, our powers didn't match up. Same thing with 1 over x, the powers don't match up. Okay? If you recall from Algebra 2, the powers of the highest exponent is called a degree. So what we're going to do is look at the different instances where this power is bigger on bottom, where the power is match, and when the power is bigger on top. So first case is we're going to look at y equals this 1 over x, which is where the power is bigger on the bottom. Okay, we know a lot about this parent function, so we know that this has a horizontal asymptote at y equals 0, but I want to talk about why. All horizontal asymptotes define the end behavior, so it doesn't tell us a restriction like vertical asymptotes do. Instead, it tells us what's going to happen in the long run. So for us, the long run is measured by an x value that's very, very large. So we're going to let x equal 1,000. This would look like y equals 1 over 1,000. And if we think about that fraction, it's really small. And it's really small, in fact, where it's close to 0. And if we keep increasing, if we keep getting larger and larger x values, it's going to get smaller and smaller, closer to 0. That's going to be true even if this was x plus 1 over x squared. Okay, this bottom number is going to be larger, way faster than this top number. So it's bigger on the bottom here, which means the result actually is smaller towards 0. And this is always. 0. Okay, that's option 1. The second option is when our powers actually match. So this one looks like maybe x plus 1 on the top, that's a line. Maybe x minus 2 on the bottom, that's also a line. Both of those have powers that are the same. Okay, and so again, to see what's going on here, what we're going to do is just pick a really big number. So this, if we do 1,000 plus 1 over 1,000 minus 2, we get 1,001 over 998. Okay, and if we add some more zeros here, we get something like that. And this continues where this fraction is really close to the number 1 because the top and bottom numbers are going to get closer and closer to identical. So it's not y equals 1 always. It actually has to do with whatever number shows out in front. Okay, if I would have changed this to a 2, this would have been 2,000, in this case 20,000, and then that would reduce to very close to 2. If this was 2 over 3, then this would reduce very close to 2 over 3. So in the case of this one, it's going to be the leading coefficient of the top part over the leading coefficient of the bottom part. So I want you to just circle the numbers in front. And if you still have the ones, that's great. Put a little 1 in there and just circle them in front because that's where the horizontal asymptote is going to show up every single time. Okay? Now I moved this over for you so you have a little bit more room here for the third type. I said it's not quite a horizontal asymptote, so I'm going to give it a separate spot. It's called an oblique asymptote. And sometimes your book refers to it as a slant asymptote. Okay, for this, it's where we have the power larger on the top. So let's write this example, y equals x squared over x plus 1. I'm adding a constant because if we just have x squared over x, that simplifies. Okay, so we're just going to think about this power. Power larger above. Okay, and doing this the same way. So this would have 1,000 squared over 1,000 plus 1. And this is much larger than this value. In fact, it's so much larger than this value, it's not approaching a single value because this one is always going to continue going up and up and up. So it's not exactly infinity. It follows a pattern of a line. Okay, but I'm going to show you about this one when we get to a specific example. What I want you to do is write y equals mx plus b because an oblique line will be in that formatting, not an x equals or a y equals. Okay, and this is going to come from synthetic division. Just like over here, this came from really these dividing this fraction, but the change over here, the extra plus and minus things, didn't really make a whole lot of difference in the long run. Here, we are going to physically divide the values that we see x squared and x plus 1, and I'll remind you how to do that using synthetic division. Last thing are intercepts, and this is real quick because we've done it already multiple times. An x-intercept we know looks like x and then 0. So all you have to do for this one is set y equals 0 and solve. And then for a y-intercept, very similar. Okay, a little bit easier with the math, 0y. You're going to set x equals 0 and simplify. So now what we're going to do is practice. We have 3 today to practice with. Plenty on your homework, and then we're going to do another day of just practice because it's going to take a little while to get good at this. We are focusing on the algebra that finds the graphical features. So we're going to do a lot of this without a calculator. Now I'll show you the relationship with the graph so you believe me that this is truly valid here. Okay, but I want you to be sure that you are doing this math by hand, okay? So we're finding the critical values, your asymptotes and the intercepts. Okay, what we're going to do is start with our asymptotes, just like we did before. Okay, so vertical, it comes from a restriction in the domain, so you're going to set this thing equal to 0. So just below here, 2x minus 8 equals 0. You're going to get so good at this where you don't have to write it out, but I do recommend writing it out for this. When we solve, 8 goes over, and x equals 4. So we're already halfway done with our asymptotes because your horizontal, the 1, 2, 3 versus oblique, there can only be one. So one of those cases is true. So we're doing that next, horizontal asymptote. We know it's y equals some number. And we're going to look at the powers to decide. Okay, so here we've got the powers where they match. Remember, if we talk end behavior, this is a really large number. A really large number, all you have to do is divide the leading coefficients. So that's going to be y is 3 over 2. Okay? And then intercepts is where a little bit of work has to happen. Okay, at least for the x-intercept. We know x-intercept has a 0 here, so we're going to go up to the original problem and put a 0. Now, this equation wasn't too bad to start with, but I'm going to have you preview the next two. Sometimes when we look at our rational functions, there are quadratics involved. And in that case, factoring is going to make our life much easier to simplify these. So what I want you to add to the top of the page is always factor first. Okay? In this case, we actually could have factored, but it wouldn't have done us a whole lot of good because we were able to solve without it pretty quickly. But I do want you to go back here and talk about this top part. Okay, there's no GCF here. We can't split it up since it's not quadratic. It stays the same. But on the bottom part, there is a GCF, so even if it's linear, you can factor if there is a common factor. And in this case, we could have taken a 2 out. And sometimes that helps us simplify the whole fraction, which we'll talk a little bit more about next class. Okay, this would have helped us see the +4 for the asymptote maybe a little bit faster. Okay. Back to x-intercept, we're setting this equal to 0. Okay, so you can use either version in this case. Okay. I'm going to use the factored form only because a lot of the ones we'll be dealing with do have quadratics somewhere. But we are multiplying over this whole thing. And I'm going to have you write it out until we get good at this process. Remember, 0 times anything is 0, which this says 0 equals then 3x plus 2. Solving this, subtract the 2 over, and use as many steps as you need to here. Divide the 3, so we've got a -2/3. It's just coincidence that these were reciprocals. It has nothing to do with a pattern that normally happens. Okay, y-intercept is a lot faster because we're not solving anything, we're just simplifying. What I mean by that is the 0 is going up in this equation, right there and right there. Everything goes away except for these constants at the end. So that looks like 2 over -8. And then we just simplify, in this case that means reduce, -1/4. Okay? And now we have everything we need to be able to graph. Now here's the thing, y'all. These items, a lot of them, can come from your calculator. However, you must be able to do these by hand. Okay, we're going to use them now to sketch all together what this rational function looks like. I said it's related to like a 1 over x because of this fraction that goes on here. Asymptotes are going to show up and we'll have branches similar to what we see there. Okay, so we're starting with our asymptotes always. We've got x equals 4, vertical. A lot of times if I have an asymptote that's so far over to the right or so far over to the left, I won't put my x-axis and my y-axis directly in the middle. I'll shift them over. If I know I need an x equals 4, I'll start my y-axis over more to the left so that this is more centered. Okay, y equals 3/2 is like 1 1/2. Put that one on there as well. And I want these to be neat, so if you're someone who can't draw a relatively straight line, please use a straight edge. Okay, on the curves, we're going to just do the best we can, but on those ones, if they don't look somewhat neat, please grab a straight edge. It doesn't take very much extra time. And now we're going to put these points on here. Okay, so -2/3 would be right over here somewhere. And we'll label it. And then 0 1/4 here. Label it again. And those were the only 2 points, but the asymptotes guide the behavior. So it starts at the end here, goes through those points, and heads towards the other one. And I said this is similar to a 1/x. It could also be similar to 1/x², but ours didn't start with that kind of action happening. What we're going to do is just think a little bit. We have options for the second part of the graph in all those 3 sections. But as soon as I put one here, this is no longer a function, so that is out. So realistically, we only have 2 options, here or here. And we have the math to show which one it is with what we've already done. There was exactly one x-intercept. So it can't be here because then it would have to cross another, at another x-intercept. And we don't have that, which means it must be up top in this quadrant. And you're just going to sketch it similar to what you see going on the other side. Let's try another one. So this time, like I said, factoring first. We have a quadratic, so we're going to do that to the side very first thing. The x plus 2 stays, and on the bottom, we're going to have to do some factoring. Okay, remember, if there is a number in front, the first thing you need to do is look for a GCF. Unfortunately, there is not one here, so you're going to have to factor. So 2 times -1 is -2. We're looking at the factors of -2 that add to be -1. Okay, so we've got a -2 and a +1. And then you can factor that however you like. Okay, I'm going to show the box method again, because a lot of people caught on to that. If you want to factor by grouping, that's also great. So here, we're starting with the 2 and -1, putting in our factors, -2 and +1, and GCFing all the way around. So here, this is -1. Here is 1. This one, a 2 can come out, and this one, a 1 can come out. Remember, you want to match the sign of the first term in your box as you go around these directions. Okay, it doesn't have to be negative for both for a negative to come out. So this factors into 2x plus 1 and x minus 1 in whichever order you like. It doesn't matter. Okay, but now that we have that, we can go start answering some questions. So vertical asymptote is a good place to start in this one. And because there are 2 things in the denominator, there are actually 2 vertical asymptotes, which is not something you've seen before. Okay, both of those get set equal to 0. First one, subtract over, divide by 2. I hope we get to a point where we don't have to write all of these little steps, but you're welcome to show as much work as you need to. This one, adding the 1 over. So we've got 2 vertical asymptotes on there. Okay, now we're going to do horizontal. That, remember, comes from the powers. So we're going to go put our powers up here. Highest one is the 1. Highest one is the 2 here. And because it is bigger on the bottom, think about plugging in a large number. The bottom's going to get bigger faster. So if this part's getting bigger, then we have a horizontal asymptote approaching 0 because the whole fraction gets smaller and smaller and smaller. So that's y equals 0. That's any time power is bigger on bottom. Okay, and now we're ready for the x-intercept, y-intercept. Okay, x-intercept, we know 0 goes here. So now we're going to go back up to our equation. 0 equals, again, factored form is better for this. So we're using x plus 2 over 2x plus 1 and x minus 1. Multiplying the whole thing over to get rid of that fraction. Okay. But when we multiply by 0, it's just 0. And solving that, we get a -2. Okay. y-intercept. A little bit easier. Okay, 0 something. And for this one, I actually prefer using the original equation. Basically, the y stuff, the horizontal and the y-intercept, I use the original form. And the other two, the x stuff, I use the factored form for. It's not wrong to use the factored form for this one, but because this is factored form, this really means times in between. You have to take a 1 times a -1. It's just easier to simplify this one. Okay, so try to remember y-intercept, use the original. All right, let's go put in those zeros. 0 here, 0 here, 0 here, everywhere we see an x. So we're left with, again, just the constant. So 2 over -1, which is -2. And now that we have all of that information, we are ready to graph. Okay, so we're starting here, and let's think ahead a little bit, like I was talking about. This time we have asymptotes kind of balanced on each positive and negative, so it's okay to have our y-axis in the middle. Okay, so we'll start with that. And then this horizontal asymptote, again, is in the middle, so it's okay for our y-axis to be there. With the horizontal asymptote being right at 0, it may be hard to see that there is an asymptote there. Just make sure you label it just like we have been doing. Okay, and then we'll add in the other two. So 1 is at 1 because we have values that are almost balanced but not really. I'm going to go ahead and put a scale there. There's my x equals 1. So if that's 1, here's 1, and the 1/2 would be here on the negative side. And I don't care whether you label on the top or the bottom side, which side, either for that one. Now let's plot some points. So we have an x-intercept at -2. Okay, so in this case, we've got right here, here's the -1/2, here's the -2. Okay, go ahead and label that one. And then we've got a y-intercept of -2 as well. Okay, so I know some things. I know that I'm not going to cross this x-axis other than this point. Same thing goes for the y-axis, because for a function you can only have one. What that means is, for this middle asymptote behavior, in general, you could have something like a parabola that goes down. Same thing up here, you could have a parabola. You could have this like cubic shape in the middle to approach both asymptotes, and it can go up or down. Because we know there are no other x-intercepts, this thing has to go down. So it has to look like a parabola in the middle. Okay, that's not something I would expect you to know. I'm telling you now. And it's not perfectly symmetrical based on this point. Okay, it's symmetrical between these two values, but you're just going to sketch roughly starting at the asymptote, hitting that point, coming back down towards the asymptote. Okay? And then we have to talk about these ends. Okay, again, we could be here or here, and same thing on this side, here or here. Now what's weird is you have an x-intercept on an asymptote. We saw that on the front side, the very first example, but end behavior does not mean that this thing only gets close to that value. It could hit it and then alternate back and forth. It could hit it and just stay below, stay above, and we're really not sure without adding some extra values. Same thing on this side. Now I do know it will never cross this again. So we're not alternating back and forth because I only have a certain number of x-intercepts. I found exactly one. So either this thing comes down and stays below, really close to 0, or it starts low and then stays above, really close to 0 the whole way. On this side, it could be either or, but it won't cross at all. Okay? What we're going to do is just take some time to use our calculator, help us a little bit with these ones when we're missing some pieces. Okay? The math to this is really just using our table. We could use the graph, don't get me wrong, but it's using our table to pick some values. So this is x equals 1. If I want to know what's going on over here, I just pick an x value of 2 and I sub those in. And all I'm really looking for is it ending up positive on the top half, or is it ending up negative on the bottom half? So in this case, it's pretty quick math here. You've got 4 on the top, and then 2 squared is 4, 8 minus 2, minus 1 is still positive, so we're going to end up on this top half. Okay, but I'm not taking away your calculator here, so we are able to use that to help us. I just want us to understand the algebra between these two things. The same thing goes here. If we want to decide what's happening, we can just pick -1, and that'll tell us if we're up here to start and then go below, or if we're down here to start and then go above. So here, if I pick -1, same concept, you plug that in, you simplify. Okay, what I'm going to have you do is go ahead and grab your calculator, clear out anything that's in there. And anytime we're plugging in, we want to use the original. And in order to use factored form, we'd have to add in extra parentheses. We don't want to do that. We already have to add parentheses around anything with 2 terms or more. So parentheses, x plus 2, close it, divided by, and then on the bottom, 2x squared minus x, and then minus 1. Oops, I got to log in there. Sorry, folks. Starting over will be a little bit more efficient here. There we go. And then we'll take a peek at the graph. Okay, we can see they're both on the top half, but I want to show you what's happening here. So go to the table for me, second table. And then we want to look at what's happening past this -2, because I told you it's not hitting this again, but we know it did touch it. So if you go on your negative side, just scroll. Okay, we see at -2, it's at 0, and then it goes negative after that, and it's really hovering around 0, very close. It just never crosses again. So here, you're going to start at the asymptote, hit it, and just barely be below the whole time after that. Okay, very strange. On the other side, it's more traditional because we know it doesn't touch, and we decided from the graph it is the top half. And really, the weirdest things with that intercepts on top of asymptotes are going to happen when you have 2 vertical asymptotes. You don't have to worry about that strange thing happening in the other cases. Okay, so we're going to look at the last case, and this is where we've got the power bigger on top, but first step is always factor. Okay, what I'd like you to do is pause the video and factor that for me. Okay, you should have gotten something like this, and then we can go to work on vertical asymptote. This is just denominator equal to 0. Hopefully this one we can see. If we set that equal to 0, it's just 2. A horizontal is not happening here because this is where there is power bigger on top. So this one instead is an oblique asymptote, and you can write that as OA. Okay, for this one, we are going to synthetically divide. So here's how this works. We want to literally do this division. In order to do it, what you're going to do is draw this upside down box for me, and you're going to just put the coefficients of the top part inside the box. So 2, 3, -2. This is for your x squared, this is for your x, this is for your constant. If there is a piece of this missing, you have to place a 0 in its spot. Okay, so this said x squared minus 1. You'd have to use 1, 0, -1. Don't forget that. Okay, then what we're going to do is divide not by the factor, but the 0 it corresponds to. Essentially, this 2 comes down every single time. It's the thing that makes 0 happen. And as a reminder, first step for synthetic division is drag down this part. Outside the box, we're going to multiply, and inside the box, we're going to add. So we're outside. 2 times 2 is 4, and we alternate. 3 plus 4, since we're inside the box. And then we're alternating again. 7 times 2 is 14. Inside, we're adding to 12. This, put a box around, it's the remainder. And then we're going to work our way up again. This is constant and single x. Because when you take a squared and divide it by a single x, it reduces down to a 2x, or a linear equation, and it's a +7. This right here is the equation of your oblique asymptote. because we talk about asymptotes, vertical ones and oblique, as end behavior, in the long run, when I put 10 million here, this remainder is not going to matter. Because a remainder, what it really is saying 2x plus 7 plus 12 over this factor of x minus 2. And if this is 10 million, this is essentially 0, and it goes away. So remainder, just cross out every single time. But this is literally a slanted line that we'll dash on. Okay, x-intercept. One thing that's going to happen with when we have these oblique asymptotes is we'll usually have two x-intercepts because there are two things on the top. Okay, let's see that in action here. We're putting 0 equals factored form for this one. This whole thing. Oops. And we're always multiplying over that denominator. I'm hoping that you're getting to this point now where you realize that this denominator will literally always go away, and an x-intercept is honestly just the numerator equal to 0. Why that's helpful is when we have factored form, we can really easily solve these. Taking opposite of this over this would be 1/2. And the next one, opposite of this, nothing in front to worry about, is just -2. And then we don't really need all this extra work if we can think about that pattern. Y-intercept has a pattern as well. When we plug in 0 to this thing, okay, remember the original is what you want to use here, all of the things go away except for the constants. So you're really just always dividing those constants. In this case, that gives us a +1. Okay, so let's talk about all of these things together. We've got a y-intercept, two x-intercepts, a slanted asymptote, and a vertical one. Because of this one, this is going to be the trickiest. You want to think about that on your graph. When we think about that, here is the 2x plus 7, and it goes up from there. This vertical is going to go up from here. So instead of having our asymptotes cross each other and we have 4 quadrants this way, we have this slanted version. We've got a v and a v over here and then the sides. So it's still going to have, we have to think about where the branches could be based on it being a function, but this tiny corner is going to be way up high. So what that matters about is if you see a positive y-intercept, you have to start your graph down lower so you have room to make space up above. Okay, so you're going to put your x-axis pretty low. Okay, and then your y-axis, in this case, we have an x equals 2, so maybe you move this over just a little bit. Okay, and because this has a slope, we're going to put a scale on this thing. So 1, 2, 3, 4, 5. This one has to start at 7, so we'll go 7 and then a few more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll see if we need more after that. Okay, from there, let's start graphing our asymptotes. First one's easiest, the x equals 2. Dash that on there for me. Okay, 2x plus 7 starts at 7, and then goes up to right 1, up to right 1, and then once you've got a couple dots, you can sketch it with your straight edge. Just make sure it's a dashed line. And do silk right there. Connecting through. So this tells us, because my v is right here, I'm going to have to erase this x equals 2 and go up higher on this part so that I can actually see more of that v. I'll just put this x equals 2 down here. I want to see a good enough portion of it because part of our graph could be there. So it could be here and here to pass the VLT, or it could be here and here. And all you have to do is look at your intercepts to decide. So our intercepts were at 1/2 and -2. So 1/2 is here. -2, based on this going down to right 1, down to right 1, down to right 1, is past 2. Okay, so we're putting it there. You can label those. And then our y-intercept was at 1. So following the asymptote, we start here, go through the points, head back towards it. This looks like kind of a sideways parabola, which means our other one has to be up here. Remember, it can't be next to it because that would cross the x-axis again, and it can't be above it because then we'd cross the y-axis again and the x-axis again, but also it wouldn't be a function. So these ones are always going to be diagonal from each other. So the other one you're just going to draw up here the same way, little sideways parabola. And that's it. We're going to practice a ton of these different types of rational functions so we can see all this different algebra and get good at recognizing these patterns ahead of time. Okay, please try this stuff without a calculator. You're welcome to use it as a backup, but I've got to see the work and see that you know the relationship between the two. And if you're stuck on your homework, please come see me.